everyone for having me. I'm very excited to be here. And before I get started, I'd like to mention that this is joint work with my co-authors, Anish Agarwal, who's also on the call. He's starting faculty at Columbia, Hara Podimata, who is starting faculty at MIT, and Stephen Wu, who's my co-advisor at CMU. And so the broad theme of this talk will be from causal inference to decision making. And namely, I think everyone here can agree that causal inference is a very important tool to use when making decisions. But there are additional challenges which come when making the leap from counterfactual inference to decision making that you perhaps wouldn't initially think about. So in particular, when decision subjects care about the decision that they receive, then they have an incentive to strategically modify their input to the decision-making process. And this has been observed across many domains. One example domain is credit lending. So you'll see articles online such as how to improve your credit fast, with tips such as pay credit card balances strategically. Another domain is in automated hiring, in which, or automated resume scanning rather, where you'll see articles saying, okay, here are the key keywords to list on the on your resume, or questions such as, is it a good idea to put keywords in white font to like win over the automated screening software? And so the research question we ask is, how do we do effective causal inference when the data may be strategically modified? And so sort of like I said earlier, the way we do this is we take tools from causal inference, which is obviously very data dependent, but doesn't normally think about incentives, and tools for mechanism design, which is in some sense data free, but deals a lot with incentives in order to do robust data-driven decision making. And so one running example from retail we'll use is that of Zara. In particular, there's this paper which looks at, redesigning distribution methods for Zara. And in particular, paraphrasing here, but they said one issue they found was the incentives of store managers, who basically had an incentive due to either compensation or promotion prospects to over request quantities of, say, shirts needed for their stores. And while this may be good to boost sales of their particular store, this could have a negative effect on the brand as a whole, if all managers do this. So you can sort of think of this as a problem between a principal, so Zara headquarters, whose goal is to maximize revenue across, say, all of their stores, and a strategic store manager who only wants to maximize sales of their particular store. And the store manager gives possibly modified sales data to Zara HQ. And then based on this data, Zara headquarters decides whether or not to assign a discount to a particular item at that store, with the goal of maximizing revenue. And so in particular, our focus is on panel data, which is time series data collected across different units. And I guess that's reflected in this running example as well. Where they use time series historical data of the article of clothing to help make their decisions. And so you might ask, what is panel data? So panel data is data from different units. So in this case, each unit is a product over time. So this would model, for example, different inventories of different products over the course of different weeks. And so our goal in this setting is to assign interventions in order to accomplish some downstream objective. So in particular, you could just think about maximizing total revenue. And so maybe, if you have a product which is not being bought very often, you may want to put it under discount in order to incentivize more people to buy it. Whereas on the other hand, if you have a product that is already very popular, it may not need a discount in order to sell well. And so one question one might ask is can this actually be a problem with real world panel data? So we do some experimental, we see if this holds empirically with an experiment on some real panel data set, which contains data about 24 products over the course of 18 months. And the prices of these products range from, say, $6 to $22 per item. And then at various times of the year, some of these products go under discount. And these discounts range from, say, $2 to $12. And so the way we construct our data set is we find periods of 5 weeks under which each unit is under no discount, and then a period of 3 weeks following it, whether it's continuously under discount or continuously under no discount. And we take these and we treat these as our particular units. So this 5 weeks of sales is our so-called pre-treatment data. Our treatment is whether or not to assign a discount. And then, since this is real data, we only get to observe one of the counterfactuals. So we use, standard methods from, called synthetic controls or synthetic interventions to impute the missing counterfactuals. And I'll get into those a bit later. And our goal here, like I said, is to assign discounts in order to maximize revenue. With the added, challenge that these store managers now may strategically modify the pre-treatment data in order to maximize sales at their particular store. So a natural approach to solving this problem, particularly in the non-strategic setting, is that of synthetic controls or synthetic interventions. So at a high level, synthetic controls is a very popular method used to learn counterfactuals under control using panel data. And synthetic interventions is a recent generalization which allows us to learn counterfactuals under control and interventions. And so to go into a bit more detail of how these methods work, suppose you have some historical data of different units, so in this case products, over different weeks. And suppose that all products are under control, so under no discount for the first 3 weeks, and then some products go under discount for the rest of the time. So say products 1 and 2 go under discount starting in week 4, whereas products 3 and 4 remain under no discount or control. And then suppose this new unit 5 comes along and you want to estimate the counterfactual trajectories both under discount and under no discount, under treatment and control. So yeah, the way these methods work is first we use this pre-treatment data, so weeks 1 through 3, to learn some representation of unit 5 as like a linear combination of, for the case of discount, units 1 and 2, because they were the ones who received the discount. So for example, you may find that unit 1 is like 30% of unit 1, or unit 5 is 30% of unit 1 plus 70% of unit 2. Step 2 then is to use this learned model and the post-treatment data of the units you've already seen to construct a synthetic trajectory of unit 5 under the discount. And then you can do something similar for control as well, no discount. But now you're going to use the outcomes of unit 3 and unit 4. So say you find that unit 5 is now like 10% of unit 4 and 90% of unit 5. Then what you would do under these synthetic controls or synthetic interventions style estimators is you would learn this model, or use this learned model and the post-treatment data from these units we've already seen to construct the synthetic trajectory of unit 5 under the discount. However, one thing to note is that since we're doing this learning on pre-treatment data, unit 5 or whoever's reporting the data of unit 5 has an incentive to modify it to make the discount look more appealing. And this can be done, for example, by artificially reducing the reported inventory levels of that particular unit in the pre-intervention period. And I guess we'll see on the next slide, this can cause the synthetic interventions estimator to perform poorly. So what we have here is we have this non-strategy proof synthetic interventions estimator, and we're comparing it to this oracle, this all-knowing oracle, which knows the best intervention for each unit. And our metric of interest here is normalized change in revenue, which the best it can be is 1. And you'll see that the non-strategy proof synthetic interventions estimator gets 0.237. So we do observe a significant drop in revenue due to this strategic misreporting. So the outline for the rest of the talk is as follows. First, we're going to formalize this principal agent problem. Then we're going to go into some of the structural assumptions that we use in order to make this problem tractable. Next, we'll talk about strategy-proof intervention policies with 2 interventions. Let's see what that looks like. And then we'll go into learning these strategy-proof intervention policies from data. We'll revisit the empirical results with our strategy-proof intervention policy in hand. And then if there's time, we'll go into strategy-proof intervention policies for 3 or more actions. Okay, so the protocol is that in which a principal, for example, our headquarters, has access to some limited historical data which has not been strategically modified. And one example in which this can arise is when data is collected through a randomized A/B test, So in such settings, there's no incentive to strategically modify because the intervention you receive does not depend on your pre-treatment outcomes. So next, using this data, the principal learns and commits to an intervention policy. So what is an intervention policy? Well, it's a mapping from pre-treatment data to assigned interventions. So sales data from a store to whether or not to assign that store a discount. Finally, new units arrive to be treated, and using our committed to intervention policy, we decide whether or not to treat them. And I guess the interesting thing here is that the pre-treatment data for these new units may be strategically modified somehow. Okay, so what structural assumptions make the problem tractable? In particular, we'll make two structural assumptions. One is on how units strategically behave, and another is an assumption on the non-strategically modified data. So we assume that units modify their pre-treatment outcomes according to an effort budget. So basically what that says is that their modified pre-treatment outcomes need to be within some bounded norm of size delta from their initial pre-treatment outcomes. And they're doing this in order to maximize their chances of getting a, I guess, positive intervention. So we assume they prefer treatment to control, discount to no discount. And this is a common assumption within the Econ CS literature on learning under incentives. And the assumption that we make on non-strategically modified data is a latent factor model assumption. So in particular, this is a ubiquitous assumption in panel data, and traditionally it assumes that the outcome you observe for a particular unit I at time t under control is a noisy snapshot of an inner product between two latent factors, one which depends on the unit only, this is vi here, and one which depends on the time step and I guess the fact that we're under control, which is ut0. So what we'll use in an extension of this, first proposed in Argwal et al., which basically extends this model to hold under interventions as well. So now the outcome you observe for some unit I at time t under intervention d is a noisy snapshot of the inner product between a latent factor which depends only on the unit and a latent factor which only depends on the time and the intervention. So you might ask, what is this latent factor model bias? Well, initially, a reward is just some possibly arbitrary function of the post-intervention outcomes, which you don't get to observe until after you have assigned an intervention. But using our latent factor model, you can actually show that you can rewrite the principal's reward, which I guess to keep in mind could be maximizing revenue, as some linear function of the unit's pre-intervention outcomes. And this is important because you observe the pre-intervention outcomes before a decision is made about which intervention to assign to a particular unit. And you may ask, okay, well, what is this for formulation bias? Well, we know that the principal wants to intervene on some unit I if the reward for intervening is greater than or equal to the reward for letting that unit remain under control. So using our reformulation, you can show that it's equivalent to this condition on the pre-intervention outcomes, where beta 1 is this linear function associated with the reward under intervention 1 and analogously for beta 0. So pictorially, what that looks like is the following. So plotting that separating hyperplane in blue in this pre-treatment outcome space, you see that it's optimal to assign intervention 0 to all units who have pre-intervention outcomes to the left of the separating hyperplane, and likewise it's optimal to assign intervention 1 to all units who have pre-treatment outcomes to the right of the separating hyperplane. And I guess this is crucially assuming that these pre-treatment outcomes are not strategically modified for the moment. So we see that units are of type 0 if the principal would prefer to assign them intervention 0, aka the control. Likewise, we say units are type 1 if the principal would like to assign them intervention 1, aka the treatment. And I guess I'd like to stress that this hyperplane is a linear function of only the pre-intervention outcomes, nothing that happens after the intervention. And so the basic idea in order to make a strategy-proof intervention policy is to shift this separating hyperplane to account for the strategic manipulations. In particular, recall our effort budget assumption, where we assume that units can modify their pre-intervention outcomes according to some bounded L2 norm. So under this assumption, we can shift our separating hyperplane by delta in order to account for the strategic manipulations. And it turns out this is actually a strategy-proof intervention policy, and you may ask why. So two parts to that. The first part is, why can't units of type 0 strategize to receive the intervention? And the answer is because we shifted it by some amount delta. So it's too much strategizing for them to receive the intervention. And the other question is, why can units of type 1 always receive the intervention? And this is because they'll either fall within the place where they won't have to modify in order to receive the intervention, or if they do need to modify to receive the intervention, they'll always need to modify by some amount less than delta, so they can always receive it. And so our theorem says that under this latent factor model and under this assumption on how units strategize, then there always exists a strategy-proof intervention policy under two interventions. And this can actually hold in settings beyond the latent factor model. I won't get into that here, but if you're interested, you can check out the paper for more details. So we've characterized the strategy-proof intervention policy, but in reality, these betas, these linear functions, are unknown. So you may hope to estimate these from historical data, which, like I said, may have been collected, for example, through A/B testing. And then what you're going to do is, you're going to have these noisy estimates of these betas, and you're going to apply this to the pre-intervention outcomes of the observed units, which is itself noisy. And so what we can show is that under this latent factor model and under zero mean noise, the error of the strategy-proof intervention policy is bounded above by how well we are able to estimate these betas. So on the left-hand side, you have your, I guess, the average difference in reward between the optimal thing to do, which is the optimal intervention for some unit I, we denote by di star, and the thing that you actually did. So the intervention given by your algorithm to unit I, we say is dia. And we show that this can be upper bounded by your estimation error for essentially the counterfactual estimation error. So what do you think the reward would have been for unit I had you actually assigned them intervention D? And so if this thing is small, then we do a good job at assigning interventions in the presence of the strategic modifications. And we can make that formal. So specifically, when we use principal component regression to learn these linear relationships, then under a strong factor assumption, this term on the right-hand side, this estimation error term, goes to 0. And just a quick remark on PCR, it's like a very popular technique for so-called error in variables regression. And so now we can return to our empirical results. And recall the performance of the synthetic interventions estimator, which was not strategy proof, did not do so well. So now with this sort of strategy aware version, which shifts the hyperplane or the learned hyperplane to account for strategic manipulations, we see that we do much better. So in particular, our normalized change in revenue is much closer to 1. And in the paper, we provide additional empirical results under model misspecification. So what we study there is, what if the principal doesn't exactly know how much a unit is able to manipulate if they just have some estimate? And we show that the performance of our methods degrade gracefully as a function of this model misspecification. Okay, so now we can move on to the setting where you have 3 or more interventions. So now you don't just have a single treatment and control, but you may have multiple treatments in addition to control. And the perhaps surprising takeaway here is that designing strategy-proof intervention policies may not be always possible. However, it is possible under, for example, a gap assumption on different rewards for different interventions. And we make this formal in the paper. But in order to give intuition as to why it's not possible, at least all of the time, consider the following scenario. So suppose that we're plotting the space of unit pre-intervention outcomes that have not been strategically modified. And suppose that under this setting, it's optimal to assign units in this left shape, intervention 0, aka control, units in this right shape, intervention 1, so first treatment, and units in this upper triangle, intervention 2. And furthermore, suppose that units prefer intervention 2 to interventions 1 and 0, and suppose that they're indifferent between interventions 0 and 1. So they don't care which of those two they want, they just want intervention 2. So one thing you might try is you might try to apply the same heuristic which we use to get a strategy-proof intervention with 2 interventions, which is, okay, let's shift the separating hyperplane to account for strategic behavior. So if we try to do that here, what we're going to want to do is we're going to shrink this region for assigning intervention 2. So in particular, you want to shrink it by delta, so no units of other types can receive intervention 2. However, if you do that, then you'll find that you've actually moved the boundary in by some amount more than delta down here. So in particular, if a unit's pretreatment outcomes fall very close to the origin, then if you shift it by this much, they may not be able to strategize enough to receive this intervention 2, which they should receive in order to be strategy proof. So in the paper, we formalize this. We provide sufficient and necessary conditions for a strategy proof intervention policy to exist. And then when a strategy proof intervention policy does exist, we provide an algorithm to learn such a policy. Oh, from historical data, like in the previous setting. Okay, so to wrap up, I guess the high-level theme and takeaway is that there are additional challenges which one has to consider under the shift from causal inference to decision-making using causal inference. In particular, because you're doing decision-making, this introduces an incentive for units to strategically modify their pretreatment outcomes. Under 2 interventions, we show that a strategy-proof intervention policy always exists, and we use shift the hyperplane. This is the basic idea there. Under 3 or more interventions, we show that a strategy-proof intervention policy may not always exist. However, when we give a sufficient and necessary condition for one to exist. And then when such a policy does exist, we can learn it from historical data, which has been collected through, for example, an A/B test in which units were not strategic. Okay, so a couple of directions for future work. The first is that of heterogeneous unit preferences. So we assumed that all units had the same fixed ordering over interventions, which makes sense in a setting such as like discounting, but may not make sense in, for example, medical treatments. So it could be interesting to relax that and see what the implications of that are. And another interesting direction for future work is that of truthful mechanisms. So if you recall, our intervention policy required some units to strategize in order to receive the intervention. However, it would be interesting if this were not necessary, although I guess proving so appears difficult. So yeah, thank you for your time, and I'm happy to answer any questions that you may have.
Thank you, Keegan. Yes, we don't have open questions at the moment, but I do encourage the audience to submit their questions. We still have a few minutes. Anish, do you have anything you would like to add, since you're also a co-author, since you're here and we don't have questions?
No, I think Keegan did a great job.
Great. Excellent. Oh, great. We do have a question now. Then just takes a moment. How does your approach translate to different principal agent settings, say moral hazard or adverse selection ones?
I guess, sorry, could you go into a bit more detail about what you mean by those? I guess I'm not an expert on the, like I've heard the phrases, but it's been a while since my.
So if the audience member who asked the question is willing to raise their hand, I'm happy to unmute you and let you speak. Otherwise, we'll have to wait for oh, great. Just 1 second. I see. How do I find there? Sorry. All right, Andre, you're allowed to talk.
Thank you. Do you hear me?
Barely. It's a little bit quiet.
Computer, just to formalize the question. So in principal agent settings, it is a microeconomic model. You have different types of incentives, different types of, say, situations of utility models and so on. So is this applicable to any micro models in contract theory or similar in principal agent settings?
Cool. Thanks for your question. I guess if I understand it correctly, I believe our results apply to any setting in which there's like a fundamental misalignment of the incentives between the principal, which in this case, in our running example, is like this online platform, and the units or the person misreporting the unit's intervention or the unit's pretreatment outcomes.
Thank you. Thanks.
Okay, I think Dominic has a question as well.
Just a practical one, and maybe you already mentioned this, but so in practice, how should I think about the delta? How should I choose it? Is there a way to like learn that from data, how much people can manipulate their pretreatment covariates or their pretreatment like outcomes, or what?
Yeah, that's a good question, and I guess one which we didn't study theoretically, but I guess we sort of studied empirically. So I guess maybe to recap the main idea, what you're doing is you're essentially making it harder for individuals to get these desirable interventions. And I guess, you know, if you're deploying this, you could use information from your domain to make an educated guess. And then at least what our empirical findings suggest is that, you know, if it's somewhat a reasonable guess, your performance won't degrade too much from if you had actually known this delta. However, I do think it's an interesting open question to say study like theoretical models of learning this delta over time.
Okay.
At least empirically, also we found that if the delta was larger than if you overestimated it, then your results were more robust versus if you underestimated it.
Mm-hmm.
At least algorithmically, empirically, that's what we found, but there's no theoretical backing for that. Yeah.
Okay. Like from a practical perspective, I would also think, at least if you have it in terms of covariates, that like, yeah, some directions are like much more easier to modify than other directions. So then it's less than like an L2 bulb, or more like some direct, like you should have some sort of or something that tells you, oh, I think here in this direction you can do a lot, but maybe your exam scores you cannot manipulate. Yeah,
Definitely.
I think the results extend for anything where you have a norm, but beyond that, I'm not sure.
Okay. Yeah. Cool, thanks.
I think we don't have any open questions and we're out of time, so I think we can wrap up.
Okay, yeah. First, thank you so much for the two interesting talks, Benedict and Keegan. I learned a lot today. Now, let's quickly wrap up. First, thank you all for coming and asking questions. And next time we're going to have Aaron Gabriel from the University of Copenhagen, who will talk about derivation and usefulness of tight symbolic causal bounds for measures of benefit in observational imperfect randomized studies with ordinal outcomes. That will be the last. Next week will be the last one for before the summer break. So hope to see you all there. Hope you have a great week and see you next week.